right, so Barry is going up by 20, okay? Now, here's his growth. If you flip over to number 4 on the next page, graph these. Graph the points. Do 2 different things, though, because you're going to graph your other chart. So, for fruit flies, do dots. And then when we do fire ants, we're going to do little stars. So you can see the difference. Okay? What kind of line is this? It's a linear line, okay? That's because, what are they doing each time? They have a constant what? They have a constant addition. All right, now, if you flip back to number 3, it shows the fire ants. So red starts with 20, then he goes to 40, then he goes to 80, then he goes to 160, and then he goes to 320. So instead of adding 20 every time, he is multiplying 20 each time. So fill in your chart. Then go over to number 4. Graph your points, except this time use stars so you can see the difference. You will have 2 common points though. All right, what do you notice about the fire ant graph? What does it have in it? It's got a bend. It's got a little curve in it, okay? What kind of graph is that? What's our topic called? Exponential. So, this is an exponential, while the fruit flies is linear. So on 5, 6, 7, and 8, how does the total number of fruit flies change each week? Well, what are the fruit flies doing? Are they adding 20? Or are they multiplying? They're adding 20. Then number 6 says, what type of function can model the fruit fly data? Well, what kind of function is that? It's linear because it has a constant, what? Constant addition. What is another word for slope? Or another words? 3 words. What? Rate of change. All right, so out beside where you wrote constant addition, I want you to put in parentheses rate of change. Because you know that's your slope. On number 7, how does the number of fire ants change each week? Well, we went from 20 to 40 to 80, 160, and 320. So what are we multiplying by? 20 times 20 would be 400. So we're just multiplying by 2s. So that has a constant, instead of a constant addition, we have a constant multiplier. Okay, because we're doing constant multiplication. So number 8, what type of function can model the fire ant data? Well, exponential. And how do you know? It has a constant multiplier. You can write constant multiplication, either one. All right, page 341. Complete the table to compare the difference in growth rates of fruit flies and fire ants. So, on your constant addition, what is it doing every time? It's just adding 20. So, in that column, all you're writing is plus 20, plus 20, plus 20, plus 20. For fire ants, it's a constant multiplier, so we're multiplying by 2. All right, number 2 wants you to write a linear function. Linear functions are written in the form of y equals mx plus b. What's m? What's it called? It's called my slope. And b is called my y-intercept. All right, so to write this equation, y equals, what's my slope, my rate of change, my constant addition? 20. So if 20x plus my y-intercept. In other words, what did I start with? I also started with 20. So that will be my linear function to describe the left side of this data. Now, what would be x? What would x be considered? Would x be considered my week or my number of fruit flies? Be my week. So I have to plug in my weeks in order to get out my population of my ants or my flies. Okay? Oops. All right, on number 3, stopping to fire ants. So remember, fire ants have the constant multiplier. So week 0, they just had 20 ants. Nothing fancy. The second week, I multiplied my ants by what number? 2. The second week, I multiplied by 2 again. The third week, I multiplied by 2 again. The fourth week, I multiplied by 2 again. So look at this process. For week 2, how many 2s do you see? Like just the number 2. You see 2 of them because you're in week 2. For week 3, how many are you going to see? You're going to see 3. For week 4, how many are you going to see? 4. For week 5, you'd see 5. For week 6, you would see 6. So every week, I'm just multiplying by an extra 2. Now, this turns out to be this equation. 2 to the x equals 20. What kind of function is that? 2 to the x equals 20. It's an exponential function. Because what does it have in the function? It has an exponent. So the exponent is my number of weeks. So if I wanted to find out how many how many fire ants I have in week 15, what would I do with that 15? Plug it in for x. So somebody put in their calculator 2 to the 15th power. Is it a very large number? Like a lot of numbers?
It's 32,768.
32,768. Oh, I thought it was going to be like 10 numbers or something. Okay. So, in 15 weeks, we would have almost 33,000 fire ants in our data. Sounds like your tail would be on fire if you stepped on those. You ever been bit by a fire ant? It's bad. My dog ate them one time. Her mouth was like massive. Like your dog eats a bumblebee. It was that times 5,000. It was bad. But she survived. Alright, let's see. Number 4 on the next page. It wants to determine if the data represents a rate of change that is linear, quadratic, or exponential. So, let me go to the workbook page. All right. So, we are looking at first, how do we know if something is linear? It has a constant what? Okay, it has a constant rate of change. But what operation is it doing? It has a constant addition. All right, let's see if you remember quadratic. What difference is the same? The first difference or the second difference? Second difference. And exponential has a constant, what? Constant multiplication. All right, so on the first one, let's look at the whole numbers. How are they getting from 2 to 8 or 8 to 32? They're multiplying by 4. So put in your calculators, 0.125 times 4. What should you get? Is that what your chart says? So, A is what kind of data? Exponential. All right, B. Go ahead and connect those lines. So let's see. The point we have is 0, 1, 2, 5, 3, 10, and 4, 17. Y'all see where I got those points from? Okay. From 1 to 5, what's it doing? It's adding 4. From 5 to 10, it's adding. From 10 to 17, it's adding 7. From 4 to 5, it is, then what? Adding 1. 5 to 7, it's adding 2. What difference is the same? The second difference. So, B could be a quadratic if they would have printed it right. All right. The next one. What are they doing from 4 to 8? 8 to 12, 12, 16, 16, 20, 20, 24. They're adding 4 every time. So, since it's a constant, what? Constant addition, then it is considered what kind of function? Linear. Good. Try 5. It just wants to know, could an exponential function model this data? Justify your answer. So you have to be looking at your y values to see if it can model. All right, from 4 to 8, what am I doing? Multiplying by 2, or I could also do what? Could also add 4, so let's just put that out there just in case. What about 8 to 24? I'm multiplying 3. Could I add 4 and get 24? No, so we know that 4 can't. We know it can't be linear because it don't go any further. What about from 24 to 48? All right, times 2. Does that have a constant multiplier? Nope. So could this model exponential? No, because there is no multiplier. All right, number 6. What exponential function represents the data given in the following table? So remember, exponential functions are written as y equals b to the x, where b is my base. So from 1 to 3, what am I doing? I'm multiplying by 3. 3 to 9. 9 to 27. Is that a constant multiplication? So what's my b value going to be? 3. So my answer is just y equals 3 to the x. This really helps us answer number 9. All right. So we know that if on number 9, you see how it says f of x equals a times b to the x. All right, well, if there is no a value, we know it has to be what number? Just has to be 1, okay? So, which is what they've done here. If I take my a value and I make it more positive, greater than 1, what do you notice about the graph? It's becoming more what? More steep. If I go less than 1, it gets more flat. After it crosses the negative sign, or the y-axis, it becomes negative, it's done what kind of reflection? What does it flip over? The x-axis, okay? So, we're trying to match the yellow dots. So, we got to keep going. All right, so for this specific one, this is just an animation. You don't have to write this one. It's just showing you that your a value makes it get steeper or more flat, okay? So now, b value, number 8, it says, the exponential function can be written as a times b to the x, where b is the base and b is greater than 0. So number 8 says, what restrictions are there on base b? Well, what does b have to be greater than? Not 1. B has to be greater than, we just read it.
0.
B has to be greater than 0. B is also called, this is important, B is also called the constant multiplier. Alright, then, number 9. They call it as the A value stretches or compresses. I want you to also write steeper or flat for number 9. All right, number 11. So first I want you to write how to write f of x equals a times b to the x, where a is the y-intercept and b is the constant multiplier. That's what CM stands for, constant multiplier. All right, so for this one, y equals, what's my y-intercept in that graph or in that chart? 10. So I've got 10 times. What is my constant multiplier? What are those y values doing every time? I'm multiplying by 3. So my constant multiplier is 3 to the x. Now, can I combine that and say y equals 30x?
No.
Why not?
30 to the second power is different than 10 times 3 to the h.
Did you got that x on there? Can't combine them. Okay. All right, go to number 12. Now, number 12 starts with 1 instead of starting with 0. So first, you have to find the constant multiplier before you can find the x or the y-intercept. So, from 80 to 40, what are they doing? All right, they're dividing by 2. What is the same thing as dividing by 2 in multiplication? They're multiplying by a half. So if 1 was 80, what is 0 going to have to be? 160. So now that you know your y-intercept and you know your b value, you can take those two things and write it in the form of y equals a times b to the x. All right, y equals, what's my a value? $160. What's my b value? Why did I put 1/2 in parentheses? So I can do it on both top and bottom. Otherwise, it might just look like this. And that's just saying that the x goes to the 1. So you got to do it to both. Okay? All right, flip over to page 347. And all you're doing here is you are identifying the y-intercept and the constant multiplier. You're not doing any math. You're just telling me which one is the y-intercept and which one is the constant multiplier. All right. On A, Kendall, what did you get for your y-intercept? 3. Good. Dallas, what did you get for your constant multiplier?
6.
Good. Lawson, what about y-intercept on B?
3/4.
Good job. Kate, what about the constant multiplier?
8.
Good. Lyric, what about the y-intercept on C?
36.
Good job. And Angel, what about the constant multiplier? Good job. Those are easy, right? Easiest thing we've done all year. Right there. All right, number 18. Now we're given the chart, and we have to write the function rule. So remember, your function rule is y equals a times b to the x. So on the first one, you're dealing with fractions. Here's the easy way. Compare your tops, compare your bottoms. So, from 5 to 15, what am I doing? I'm multiplying by 3. So on my numerator, I've got a 3. On my denominator, I'm going from 8 to 32. So I'm multiplying by 4. Same thing again. From 15 to 45, I'm multiplying by 3. And on the bottom, I'm going from 32 to 128, so I'm multiplying by 4. So now, you have your y-intercept, and you have your constant multiplier. So my a value is what, Megan? It's my y-intercept. When x is 0, 5 over 8, times, what's my constant multiplier? 3/4, but what do I have to put around 3/4? Make sure you keep your x up top. All right. Now, on B. What is, if you cannot figure out, I think I just poked a hole in my pants. I sure did. Sorry. If you cannot figure out your multiplication, what can you do? You can divide. You're going to divide frontward, you're going to divide backwards. You're going to divide backwards. So on one like this, how many of you know off the top of your head what it's multiplying by? Just by looking at the decimals. Okay, a couple people. Okay, so if you don't, all you got to do is type in 0.1 divided by 0.01. And then it'll give you your answer. If you don't know. Hmm? So, what is it?
10.
So, you're multiplying by 10. So, now, you write the equation. What's my A value? 0.01. My constant multiplier is 10. And be sure to keep that X. Alright, now on C, all we're doing is we are determining the y-intercept and the constant multiplier. It has no numbers, but that don't really matter. Still in the same form. So, what is the y-intercept going to be? What over what? M over N. What's the constant multiplier going to be? Over P. Still in the same form. All right. Next, this is my favorite stuff right here. Page 350. Number 6. We are talking about compound interest. Okay? So, compound interest is used for many, many, many things. Okay? A lot of times it's used for retirement. You heard your parents talk about a 401k. How much money they're going to have when they retire from their jobs. That money's found by using these formulas. Okay? So, Agile Mind tells us that the formula for calculating compound interest, well, what? Oh my goodness, is right here. That is right, but they don't include an extra step that I'm going to include to make it easier. Okay? So, on number 6, I want you to write A equals P times 1 plus R over N times NT. Now, what is the difference between my equation and their equation? Mine have ends, okay? Oh my stars. All right, here's what all these letters mean. You want to write this down too so you remember. A equals account balance. P equals my principal balance. What's the difference in my account balance and my principal balance? If I ask you how much money's in your savings account, you're going to tell me an overall what? An overall total, okay? An overall big number. All right, if I just ask you for your principal balance, that's just kind of like me asking what's in your pocket right now. What are you starting out with? Okay? All right, R stands for my rate. T is the years. And N is how many times over a year. So, for example, if it says it is compounded monthly, how many months are in a year? 12. If it says it is compounded weekly, how many weeks are in a year? 52. If it says it is compounded daily, how many days are in a year? 365. We're not dealing with leap years. Just plain Jane years. If it says annually, annually is just what? Just one. It's okay.
It's been loading for 30 minutes.
It's okay. I would suggest writing out the formula first and then going back in and typing it in. So annually was $12.59. Monthly was $12.70. Weekly was $12.71.01, and daily was $12.71.22. So, did it grow any? Yes, it did grow. It grew the whole time. But what do you notice? The last two, the weekly and the daily, how much did it grow by? It only grew by 21 cents. So the moral of the story here is that it did grow. I guess that would be grew. From n equals 1 to n equals 365. But towards the end, what kind of state is it reaching? Like the numbers are becoming what? Not constant, but they are. Starts with the S. Close. Steady. I just knew y'all would guess it. All right, but they're becoming to a steady state. So, it all depends. There's no right or wrong way to do this in like a real life situation, like when you are doing your 401k or whatever. But it's going to depend on what you're putting in and your rate. Rate's a big, big thing. Okay? All right. What time is it? Oh, it's only, dang. Okay, let's try to do these. Okay, go to number 17. Page 353. All right. Now, this section is called E. Okay? On the E, it says, what is the value of E? Here's the E value right here. What kind of number is that? Rational or irrational? Irrational. It's just a crazy decimal. Do you have to remember that decimal, you think?
No.
I would remember 2.71. What I would remember this right here. What I've got written on my paper. E is approximately 2.71828. So write that value of E down on number 17.
The whole thing?
Yeah.
Dang, go.
You're not actually gonna write the whole thing, right?
Huh?
You're not actually gonna write the whole thing.
Yes,
I
you
just
might.
did.
Yeah, you might want to know it sometime.
Alright, leave
You
No,
said
write
we
it down
didn't
right now.
know it. The entire.
it. You said we didn't have to know it.
2.71828. It's just 5 more numbers. 28459.
Wait.
You skipped 1 8.
Oh. 7 more numbers.
Oh my.
All right. When is this used? This is used for growth and decay problems. So you would use that in like biology, doing research. But the big one here is when where's it at? Is it written on here? When it's your interest is compounded continuously. So make sure on 18 you have compounded continuously. All right, now, number 19. What formula represents continuous compounding interest? I call this PERT. P-E-R-T. PERT. Anytime you see the word continuously, you have to use PERT. Okay? Any other time, you use the long one. I don't have a fancy name for it, just the long one. But when it says continuously, you must use the per. Okay? So on number 20. What would Rachel's parents find their balance to be after 3 years if they place the $1,000 gift in a savings account that compounded continuously at 8% annual interest rate? So, for all of these, P still means the same thing. P is still your principal. E is on the calculator. You don't have to type that number in every time. So to find the E on your calculator, second LN. Do you see the second LN on the calculator? You don't have to type in the number every time. R is going to be my rate, and T is going to be my years. Okay?
I was looking for LM on the calculator.
Huh?
I was looking for LM on the calculator. Oh, wait, it's on there.
It's on there. The natural log. Third button from the bottom. Yeah, you will when you type in the problem. All right, so our problem for 20.
Never mind.
All right, we're doing continuously. So P E R T, PERT. RT's in the exponent. Okay? So, what is our principal value in number 20? What are we putting into our savings account? We're putting in $1,000. Now, all we're doing is we're plugging in that little E. What is my rate? It's 8%, so in a decimal it's going to be,
Or 0.0.
yep. And my years is 3. So, you go over here to your calculator. You all type in 1,000 second LN to put in that E. 0.08 times 3. And you should get $1,271.25. Now, how much did that change from the other ones? How many cents did it go up? It just went up 3 cents. So it just makes a little difference. All right. From now until the bell rings, got 5 minutes. I want you to work on 24, 25, 26.